Hi, today we are going to look at AP Physics 2 2024 free response questions. Just a reminder, the College Board used more than one version of papers in the exams. The version we are going to look at is the one which was published in the official website. Here's the first question of AP Physics 2 2024. We can see it is about photoelectric effect experiment. Let me read the question problem statement for you quickly. In each trial of photoelectric experiment, a scientist used a device to shine light of a single frequency on two different metals, 1 and 2. The device can emit light with frequency Fa, Fb, or Fc. Each frequency of light is used to test both metals. The scientist determines the minimum de Broglie wavelength of the electrons ejected from the metal in each trial of the experiment. The following table summarizes the results of the experiment. For each trial, the scientists analyze only the electrons with the minimum de Broglie wavelength. Here we can see the table. Alright, three different frequencies, Fa, Fp, and Fc were used. They were exposed on metal 1 and 2, and we can see sometimes electrons were ejected, and sometimes, particularly in the trials numbers 3 and 4, no electrons were ejected. Alright, here comes the first question. In a coherent paragraph length response, indicate which frequency, Fa, Fp, or Fc is greatest and which frequency is least. Justify your answer using physics principles. Before we start analyzing the table, let's quickly recap about the photoelectric effect. Now, the photoelectric effect states that when a light is exposed, when a light strikes a metallic surface, it is possible, not always, but it is possible to eject electron from it. But it depends on several factors. First, the energy of the coming light, coming photon. The energy can be also expressed as Planck's constant times frequency. Now, the energy of the light should be at least equal to the so-called work function of the metal. Now, work function is, as analogy, I say it is the price that needs to be paid to the metal to take electron from it. So, logically, the energy of the light should have at least work function energy to take electron from it. If it is less, no electrons would be ejected. If it is more, it is possible to transfer the X2 energy to the electron in the form of kinetic energy. And the maximum kinetic energy that the ejected electron can have is equal to, logically, energy of the photon coming minus the work function. All right. Now let's compare the frequencies. Now we can see that the frequency is directly related to the energy. That means if you have higher energy, we have got higher frequency. Less energy, less frequency. Good. Now, let's start with the least frequency because it's easy to see from the table. We can see that frequency B, trials 3 and 4, when this light was exposed on the metals, no electrons were ejected. That means energy of frequency of light B was the smallest. It was not enough to overcome the barrier. So let's start from there. Energy of a light is directly proportional to the frequency. We can add the equation here. Energy is equal to Planck's constant times frequency. Since light with frequency B could not eject electrons in both metal 1 and 2, it must have the least energy. Therefore, Fb is the smallest. Okay, this was easy part. Now, we have to compare what is left, A and C. Now, to do that, let's choose trial number 1, when Fa was exposed on metal 1, and trial 5, when Fc was exposed on the same metal. And we can see, and we can compare the Broglie wavelength, and we can see that When Fc was exposed on metal 1, de Broglie wavelength was smaller. So how can we use this information to compare frequencies? Here, we must remember the de Broglie wavelength equation, which is equal to Planck's constant h over momentum, which can be written as Planck's constant divided by mass times velocity. So we can see that de Broglie wavelength is inversely proportional to the speed. So if we are having smaller de Broglie wavelength, Fc is resulting in smaller de Broglie wavelength, it means that the speed of the electron would be higher. And if you remember, kinetic energy is related to the speed square of the speed. Kinetic energy is equal to half mv square. That means more speed, more kinetic energy. So here, logically, we can see that Fc is resulting in higher kinetic energy. So when we can say when the lights with Fa and Fc were exposed on the metal 1, Fc resulted in lower minimum de Broglie wavelength. Now, speed is inversely related to the de Broglie wavelength. Let's shorten it. Thus, Fc is resulting in higher speed. Since K max is related to speed square, Fc is resulting in higher Kmax too. What does this mean? Initially, the energy of light C was higher. As a result, we are talking about same metal 1. That means work function is same, but we are resulting in higher kinetic, maximum kinetic energy with Fc. That means initial energy was higher. That means the frequency was higher. So let's summarize. So if Fc is bigger than Fa, and Fb is the smallest among them. So Fa is the highest, then comes, Fc is highest, then comes Fa, and the smallest one is Fb. Alright, next question. Calculate the maximum kinetic energy of the electrons ejected from metal 1 in trial 1. Assume that the momentum P of an ejected electron can be described by the classic definition is equal to mass times speed. Okay, let's start. Actually, we wrote it above, but let's write it one more time here. Is equal to P. De Broglie wavelength is equal to h over mv. From here, we can rewrite the equation for speed, which is equal to Planck's constant divided by mass times wavelength. So since kinetic energy is half mv squared, let's bring this into this equation. So kinetic energy becomes half h squared divided by m wavelength squared. Next, substituting numbers. So we have half Planck's constant from the formula sheet. You can see it is equal to 6.63 times 10 to the power of negative 34 joule times second to the square. And mass of the electron can be also found from the formula sheet, which is equal to 9.1 times 10 to the power of negative 31 kilogram times. Now, from the table, we can see in the trial 1, the wavelength is given as 6.9 times 10 to the power of negative 10. So 6.9 times 10 to the power of negative 10 meter square. Now, the rest is the calculator's job, and it's equal to 5 times 10 to the power of negative 19 joules. All right, which you can convert to electron volt. You should divide by 1.6 times 10 to the power of 19, which gives you approximately 3.13 electron volt. Okay, done. Part C. Indicate whether the work function of metal 1 is greater than, less than, or equal to the work function of metal 2. Justify your answer by referring to the table of results. Now we have to compare work function of metals. To do that, we have to choose some trials. 3 and 4 is not useful here because no electrons were ejected. So we have to choose somewhere 1 and 2 or 3, 5 and 6. Let's choose 1 and 2 because we are having the same frequency, Fa, but we are having different metals and we are having different de Broglie wavelength. Now, if you look, we can see on metal 1, when Fa only was exposed, we are having on metal 1 smaller de Broglie wavelength. If you remember, earlier we talked that smaller de Broglie wavelength means higher speed, means higher kinetic energy. All right. So the Kmax is related to 1 over de Broglie wavelength square. When the light with Fa was exposed on both metals, in metal 1, electrons did have smaller de Broglie wavelengths and higher maximum kinetic energy. Now, since work function is equal to energy of the light minus maximum kinetic energy, metal 1 has a lower work function. Because it's having a lower work function, it is letting electrons ejected having more kinetic energy. All right, this is the end of the first question. All right, AP Physics 2 2024 free response question, second problem. We can see this is a thermodynamics problem. So let's read the problem statement. In experiment 1 shown in figure 1, a sample of an ideal gas is contained in an insulated sealed chamber with thin rigid walls. The chamber contains a heater and sensors that measure the temperature and pressure of the gas. A student is asked to design an experiment to determine the number of molecules of the gas contained in the chamber. So this is a rigid container, so volume is constant. Also, we are having two sensors here. One is, let's say, pressure and one is temperature. Good. Here's the first question, part A. Describe a procedure for collecting data that would allow the student to determine an experimental value for n. Provide enough details so that a student could replicate the experiment, including any steps necessary to reduce experimental uncertainty. Very well. Now, to understand what quantities need to be measured, we have to bring down an equation. This is gas question, thermodynamics gas question. So let's bring the ideal gas law. PV is equal to number of molecules times Boltzmann constant times temperature. Now here the volume is constant, number of gas constant, and Boltzmann constant is of course constant. So what is left is pressure and temperature. So the student needs to measure pressure and temperature. And very good thing, there is a heater already set up. So using the heater, student can change the temperature, and also we are expecting as a result the pressure is going to change. Now, first thing in experiment setup, experimental procedure is preparing the experiment, setup part. Now, because everything is set up, no need to change. But there's one thing at the beginning which can be done is the measuring the volume. Now here, how can a student measure volume? He can measure volume by he can calculate volume actually by measuring the dimensions of the container. Let's write that. Calculate the volume by measuring dimensions. We already know that the volume can be calculated by measuring the width, length, and height of the container. Now, the second part is action. The action here is the student needs to turn on the heater. All right, we assume that the heater slowly heats the gas molecules and the temperature rises. As the temperature rises, record. Now, students need to record some data. Record pressure and temperature. Now, this should be done systematically. So let's introduce a rule. Let him measure in every 10 Kelvin interval. As the temperature rises by 10 Kelvin, let him measure, let him record the pressure and temperature on a table, let's say. Let him take the measurement for several times, like at least do this at least 10 times, let's say. All right. Now he has got some data, but to increase the accuracy, let him do one more thing. Let him stop the heater. So we assume, because the walls are thin, the temperature of the gas slowly cools down. While the gas is cooling down, let him measure the pressure and gas at the exact temperatures that he recorded during the heating up. So, to increase accuracy, repeat the measurement of P and T in reverse. Let the gas cool down slowly. Measure the pressure and temperature at temperatures indicated in the heating process. All right. Part B. On the following axis, sketch a curve or line to represent the expected relationship between the pressure and the volume of the gas while the heater is on. Draw an arrow on the curve or line to represent the direction of the resulting thermal process. Now, because the walls are rigid, the container is rigid, the volume does not change at all during the process. But at the beginning, when the gas was cold, the pressure was low, and as temperature increased, the pressure also increased. So let's say at the beginning, the state was at this point. And what happened? The volume stayed same and the pressure increased, and it reached this point, second point. So this is the first state, this is the second state, and arrow represents the transition from first state to the second state. Next, on the following axis, sketch a curve or line to represent the expected relationship between the internal energy and the volume of the gas while the heater is on. Draw an arrow on the curve or line to represent the direction of the resulting thermal process. Now let's remember the internal energy equation, which is equal to 3/2 number of gases, Boltzmann constant, temperature. Now, when the gas was heated, obviously the temperature increased. But again, because it was a rigid container, the volume didn't change, the volume stayed same. So let's say at the beginning, again, our state was here, the beginning state, let's indicate with 1, and as temperature increased, the internal energy increased. So it reached, let's say, this point, state 2. it went from state 1, state 2. The arrow is representing that. Last, briefly justify why the curve or line drawn in part B second has the shape that you sketched. Now in part B second we have a straight line which is going up. So what can we say about this? Let's start with indicating about volume. The volume is not changing since the container is rigid. However, the internal energy is increasing since the temperature is increasing. Therefore, the graph has line form, moving from low internal energy to high internal energy. All right. Continuing. In experiment 2, shown in figure 2, a liquid filled container that is completely wrapped with a material of uniform thickness 0.01 meter is inside the sealed chamber that is filled with an ideal gas. The material has a total area of 0.06 meters square in contact with the gas. The heater is turned on. As the temperature Tg of the gas increases, the following data for the temperature TL of the liquid and the rate Q over delta time of energy transfer are collected. Here we can see the table and the collected data. Part C. The student is asked to determine an experimental value of the thermal conductivity K of the material used to wrap the container inside the sealed chamber. Indicate what measured and or calculated quantities could be graphed to yield a straight line that could be used to calculate an experimental value for the thermal conductivity K of the material. Use the blank columns in the table to list any calculated quantities you graph in addition to the data provided. So, what is the question covering these all quantities? The energy transfer rate Q over change in time is equal to, from the formula sheet you can see, if you don't remember this equation, conductivity times the area times the temperature difference over thickness L. Now here all these three quantities are constant. What is left is energy transfer rate and the difference in temperature. So it is very similar. It looks very similar to a linear equation. So y here on y-axis can be plotted energy transfer rate, and on x-axis it is difference in temperature. So Q over delta T and difference in temperature delta T. So on the table we have to calculate this. So 295 minus 295 0, 528 minus 323 is 205 if I am not wrong. Now next I think the plotting graph. So Q over delta T, unit is joule per second, temperature difference in Kelvin, let's say. What is the range for change in temperature? Difference in temperature is from 0 to 205, and for energy transfer rate it is from 0 to 75. Good. So both of the cases start from 0, goes to 200 on horizontal axis, so we can say 50, 100, 150 to 100, and from 0 to 75 we can do 15, 30, 45, 60, and the last line would be 75. All right, putting dots, first one is 0, 0, second one is 60. Next one is 117, or last one 205 to 75, it should be here. All right, we have got the dots, and the next one is going to be drawing straight line. Okay. We are done with the graph. Part D. Using the best fit line, calculate an experimental value for K. Okay, earlier here we wrote the equation. From there we can see that the M slope is going to be conductivity area divided by L. So slope of the graph, let's say it's M, is going to be Ka over L. From there, conductivity is slope times L divided by area. Now let's quickly calculate the slope here. We are going to use 2 points from the graph. Let's choose easy points. So 0, 0, this is our point 1. And I can see where we have a good point. Like here, I think we have got intersection. So point 2. So it's going to be 54 minus 0 divided by 150 minus 0. Now let's put this number here, 0.37 joule Kelvin second times thickness is 0.01 meter divided by area 0.06 meters square. So if we do the calculation, it's going to be 0.06 joule over Kelvin meter second. Alright, this is AP Physics 2 2024 free response questions, the third problem. This is a circuit problem. A circuit consists of an ideal battery of EMF epsilon and 4 identical resistors R1, R2, and R3 and R4, each of resistance R, as shown in figure 1. For parts A first and A second, express your answers in terms of numerical values epsilon and R only. Derive an expression for the current I1 in the resistor R1. So we have to find what is the current one passing through R1. We can see that the R1 is located on the main line. The same wire is passing through the battery. So if we can find equivalent resistance of all resistors, we can calculate easily the current passing R1 using Ohm's law. So let's start with equivalent resistance of R3 and R4. Because they are in series, we just add them up. R3 plus R4 is 2R, because each one is R. Now R3 and 4 are parallel to R2. So equivalent resistance of R2 3 is going to be equal to 1 over R2 plus 1 over R3 4 to the power of minus 1. Let's put the numbers. 1 over R plus 1 over 2R is 1. So it's going to be 3 over 2R. It's going to be 2R over 3. Now all these are 2, 3, 4 are in series to R1. So total equivalent resistance of all resistors is going to be R1 plus R2, 3, 4. So R plus R over 3, it's going to be 5R over 3. Alright, we have the R equivalent. Now we can use Ohm's law to find current on 1. Current on 1 is going to be equal as the current on the battery. The battery has got voltage of epsilon over R equivalent, so it's going to be 3 epsilon over 5R. Next, derive an expression for the current I3 in resistor R3. So we have to find what is the current passing through R3. Now, before going on, let's define some potentials. Let's say the potential R2 is dV2 and potential across resistors R3 and 4 dV3 4. And of course, potential across R is going to be dV1. So we already know the current 1 and resistance 1. So we can start from there. Potential across the resistance 1 is going to be current 1 times R using Ohm's law. So it's going to be 3 epsilon over 5. Next, potential across second resistance is equal to potential across the resistors 3 and 4 combined, because they are parallel to each other. They are all going to be, if you use Kirchhoff's loophole, the battery voltage epsilon minus potential across resistor 1. So it's going to be 2 epsilon divided by 5. Now we can use again Ohm's law. Potential across 3 and 4 going to be current passing through the resistance 3 times equivalent of resistors 3 and 4, because we are looking at the potential difference across both of them. I3 is going to be potential difference divided by resistance, so it's going to be 2 epsilon divided by 5 divided by 2R, so it's going to be epsilon over 5R. Next, part B. The partially completed bar chart in figure 2 shows a bar that represents the absolute value delta V of the potential difference across the ideal battery. In figure 2, draw a bar to represent delta V across each resistor relative to the EMF epsilon of the ideal battery. Good. The height of each bar should be proportional to the value of delta V represented by that bar. If delta V is 0, write 0 in the column. Now, earlier, we already found what is the potential across resistor 1, resistor 2, and 3, 4 combined. We already know that delta V1 is equal to 3 epsilon over 5, and delta V2 is equal to delta V3, 4 combined, 2 epsilon over 5. So let's start with R1. It's going to be 3 over 5 epsilon. R2, 2 over 5 epsilon. And R3, together they are making 2 epsilon over 5, but they are in series. So, and they are having the same resistance. That means they are equally sharing the voltage. So each one will have epsilon divided by 5. A student claims that the rate at which energy is dissipated power by the circuit can be expressed as E is equal to 3 epsilon squared divided by 5R. Part C. State whether the expression for P is correct or incorrect. Justify your answer by referring to derivations from part A or the bar chart from part B. Now let's remember the power equation. Power is current times voltage, right? If you want to eliminate current, Ohm's law, current is equal to potential difference divided by R. In that case, it's going to be potential difference square over R. So generally the form looks okay. But what about the quantities? So we have got in the battery the current which is equal to 3 epsilon over 5R, and the R equivalent is equal to, the current is 3 epsilon over 5R, and changing potential equal to just epsilon. Perfect. We can just use that to justify our answer. So in that case, we have current 3 epsilon over 5R and change in potential as epsilon in the main battery. So if you multiply them, we are having the same result. So yes, the expression is correct. Battery is producing power which is equal, E is equal to current times change in potential. From part A, we see that current was equal to 3 epsilon divided by 5R, and change in potential is equal to epsilon. Therefore, power is equal to current times potential difference, which is equal to 3 times epsilon square divided by 5R. Next part. When the ideal battery is connected in the original circuit, the rate at which energy is dissipated by resistor R1 is P original. The ideal battery is now replaced with a non-ideal battery of EMF epsilon and internal resistance small r to form the new circuit shown in the figure. So we can see that there is another resistance small r in the circuit. The rate at which energy is dissipated by resistor R1 in the new circuit is P nu. Indicate whether power nu is greater than, less than, or equal to power original. Well, now here we can use again the power equation, which is current times potential difference, or if you want to eliminate the potential difference, it's going to be current square times R. Now, if we are adding a resistance to the circuit, logically we are increasing R equivalent. And because we are increasing R equivalent, we are reducing the current on the main line, on the battery, which is also passing through R1. So because we are reducing the current, but resistance of R1 is staying same, power dissipated by R1 is going to be less than the original one. So answer is this. Let's justify it. The internal resistance R reduces the current flowing on the circuit. Since power is equal to current square times R, the energy dissipated by R1 in the new circuit, which is P nu, will be less. Done. Alright, this is AP Physics 2 2024 free response questions, the fourth problem. Two particles, 1 and 2, have different mass and charge as described by the following. Particle 1 has mass m and negative charge, negative q, while particle 2 has mass half m and positive charge, double q. In separate trials, a device is used to accelerate each particle in the negative y direction from rest through a potential difference of absolute value delta v. The polarity of the potential difference can be adjusted so that the particle with either positive charge or negative charge can be accelerated in the negative y direction by the device. The gravitational effects are negligible. After moving through the potential difference, particle 1 and 2 exit the device with kinetic energies K1 and K2 respectively. First question, calculate the ratio K2 to K1. Alright, now at the beginning, charged particles are at rest. The potential difference is interacting, the charge is interacting with the electric field produced by the potential difference and accelerated. So here, the work done on the charge is resulting as kinetic energy, work kinetic energy theorem. So here we can say that work done, let's say absolute value, let's get rid of the negative positive signs. Absolute value of work done on first particle is going to be gain in the kinetic energy of the first particle. Since we are starting from zero speed, so it's going to be kinetic energy of the first particle at the end. So work done on the charge, again absolute, let's say the absolute value can be calculated by multiplying the charge to the potential difference. In the first case, it's going to be Q times delta V. Similarly, for the second charge, the work done will be equal to K2, which is going to be equal to, here we say Q1 delta V1, Q2 delta V2. In both cases, delta V's are same, but charges are different, so it's going to be 2Q delta V. Now, question is asking us to find the ratio of K to K1, so it's going to be 2Q delta V over Q delta V. These quantities cancels, answer is 2. Alright, next question. After exiting the device, the particles enter a large region of constant uniform magnetic field of magnitude B0 that is directed in the positive Z direction, out of the page direction. Each particle is moving in the negative Y direction when entering the region, and each particle is moving in the positive Y direction when exiting the region. So they are doing half circle in the region and exiting in the opposite, moving in the opposite direction. All right, part B. Determine an expression for the speed of particle 2 in the region. Express your answers in terms of capital M, K2, and physical constants as appropriate. All right, let's start with the kinetic energy equation. Kinetic energy is half mv squared. So if you rearrange the equation, speed is going to be equal to 2k over m. Okay, what's the kinetic energy of the second particle? It's K2 divided by the mass is m over 2. So in that case, it's going to be 40 goes as times 2 to the up, so 2 times 2, 4. We can take it out of the square root. It's going to be 2 times square root of K2 over m. Part B, second. Derive an expression for the horizontal distance delta x between the locations where particle 2 enters and leaves the region. Express your answer in terms of capital M, Q, K2, B0, and physical constants as appropriate. Okay, now the magnetic field is outwards, the particle is moving downwards at the beginning. So if you are going to use right hand rule, so we will see that when the particle enters, it will experience force to the left like this, and let's assume the particle is going to move something like that. Now, the distance is going to be same all the time. And this distance, we know that it is a radius. So another radius, 2 radiuses makes delta x. So delta x is equal to 2 radiuses. All right, we can use the radius concept from the, magnetic force. Because magnetic force is the only force acting as centripetal force there. So magnetic force QVB is acting as centripetal force, which is mass speed square over r. From there, r radius of the curvature is mass times speed divided by QB. Okay, so in that case, delta x is going to be 2 times mass speed over QB. Let's substitute the quantities. So it's going to be 2, mass is mass over 2, divided by speed. Above we found it as 2 again, times square root of K2 over m, divided by the charges, again 2Q times magnetic field strength B0. So here we can see all 2's are gone. As a result, let me write it here. Delta X is going to be equal to mass times, let me say, mass over Q B0 times K2 over M in the square root. So this is our answer. Okay. Part C. On the following diagram in figure 2, sketch and clearly label the paths of both particles 1 and 2 in the region. Well, we have to compare delta x1 to delta x2 because particle 1 and 2 are having different signs and different masses and different charges. Now we already calculated delta x for 2. We forgot to label. Let's label. Oh, it's already saying delta x in the question, so I will just leave it like that. But in the next question, I will label as delta x1 and delta x2. So this is our delta x2. So let me, where do I have space? Here I have space. So delta x2 is equal to m over q b0 in the square root of k2 over m. Now, K2 here is not comparable with K1 directly, so we have to open that. So we will replace K2 with the quantity that we found at the beginning in part A. So K2, we can see it's 2 times Q delta V, and K1 is Q times delta V. So I will use that equation here. So delta x2 is going to be equal m q b0 square root of 2 times q delta v over m. Similarly, if you do the calculation for delta x1, you will follow the same steps. One more time you calculate, and I found it's going to be 2m q b0 to q delta v over m. Now, my point here is we can see delta x1 is going to be 2 times bigger. So let's start with, again, with positive charge, which is the second particle. Best on paper, maybe it's even better. I'm doing it on my iPad. So it's going to move in this direction, and the distance is delta x. Let me label as 2. Now this is for positive charge. Negative charge will obviously feel force in the opposite direction and will do a circle in the opposite direction. But the point is it must be 2 times bigger. So if it is coming here, it must be coming somewhere here. So we will do our best to draw depth. So this is delta x1. So the point here is delta x1 is equal to 2 times delta x2. And it's going to move like that. Part D. A uniform electric field is added to the region such that particle 1 of negative charge travels with constant speed in a straight line through the region. Determine the direction of electric field. Now, when negative charge is entering, let's assume this is our negative charge, negative Q, it's feeling force at the beginning towards right. This is magnetic force on it. So obviously the electric field should make it move in the opposite direction. It should be, let's say, let me draw it one more time here. So particle is here and it is negative Q. Magnetic force is to the right. Electric force should be to the left. So what kind of electric force, what kind of electric field can make the force, electric force to the left. Let's just throw imagine electric field. So if it's going to be directed to the right, like that, the electric force is going to be to the left. So E field must be to the positive X, which is right direction. All right, done.